Hey guys, I have your notes here for section 6.4, and this is a really cool section because you get to do stuff with your graphing calculator that you never knew was even possible. So we're going to do some polar graphing on our graphing calculator. Now, don't start copying any of this yet. We'll get to this later. I first want to just introduce you to what is a polar graph and how is it different from all the graphing you've ever done before. So a polar graph, instead of having x comma y coordinates, a polar graph has r comma theta coordinates, where r is the radius and theta is like the angle of revolution. And all of these points fit in a polar equation. Okay? So here's what you're used to. You're used to being in function mode in your graphing calculator, and all of your equations are basically set up y equals. There's an x involved and there's a y involved. Well, now we're going to be in polar mode, and I'm going to show you how to change the mode on your graphing calculator. And instead of having an xy table, we're going to have a theta and an r table. Now, before we get started, I'm going to jump back to the very back page. There's a lot of information back here. Don't worry, you don't have to memorize all of it. Only very little of it do you have to memorize. But these are the types of polar equations and their corresponding graphs, like what the graphs look like. So first of all, let me show you what a polar equation looks like. Here's an example of the polar equation that would graph a circle. And notice that instead of y equals, we have r equals. And instead of our variable being x, our variable is theta. So we're going to have a theta in our equation, and it's going to equal r. Now, any other variables that you see are just a constant. So this just represents some number, any number that could be out in front of cosine. But theta is our variable here. So, for example, here's an equation of here's a polar equation whose graph is a circle. A is the constant here, that's 2. Theta is our variable. Another one could also be r equals any constant times sine of theta. So any constant times sine of theta. This would graph a circle. How are they different if one of them's sine or one of them's cosine? Well, take a look at the pictures here. If it's cosine of theta in your equation, your circle actually touches the origin. It's not centered at the origin. It actually passes through the origin, and it kind of rests on the x-axis. If your equation involves sine of theta, again, your circle passes through the origin and it kind of rests somewhere along the y-axis. This type of equation produces a circle. Next up, and I'm probably going to butcher this. This is a French word, and I took Spanish. So I think it's a limison, something like that. And here's what the equations look like. R equals. Yeah, it's got a cosine in it. Might have a coefficient out in front of the cosine, some constant that's multiplied. And it's plus or minus, it's got some other constant added with it. Produces a limison. Or you could have sine in here, maybe a constant, but some other constant being added to this term. And here's what they look like. They're round, almost circular shape. They might have an inner loop. And if they do, this is what the equation would look like. And A would be less than B. It might be a cardioid, which kind of looks like a heart. This is what the equation would look like, and A would equal B. A dimpled limison, and this is what your equation would look like, and A would be bigger than B, but not as big as twice B, or a convex limacone. And this is what your equation would be, and this is the relationship between A and B. Next up is a rose. These are my favorite. I like watching them being graphed. We do stuff with these types of graph. Well, we do stuff with all of them in calculus 2. It's really cool, some of the stuff we get to do with these in calculus 2. So this is what your equation looks like. This looks very similar to the equation of a circle. However, instead of just being a constant times cosine of theta, now we have another constant in here with our angle. So this might be like r equals 3 cosine 5 theta. And that's going to produce a rose. And same with sine. Okay? Two things to notice about graphs of roses is notice the length of each petal and the number of petals. So notice the length of the petal, and there are 4 petals. We're going to be taking a look at that specific to some of the equations. And then these two, this one looks like the infinity symbol. This is what the equation looks like. Or a spiral, and this is what the equation looks like. So, I encourage you, if you have some free time, just kind of play around with your graphing calculator, make up some of these, make up your own constant and graph some of them and just kind of see what your calculator can do after I show you how to set up your calculator for polar graphing. Keep these notes handy. You're going to be referring back to them a lot as far as you're going to be able to look at an equation, a polar equation, and be able to identify, oh, okay, it's this type of graph. So keep these out and handy. Now, going back up here, you need your graphing calculator. If you don't have your graphing calculator in front of you, turned on, ready to go, pause the video and go grab it. You need your graphing calculator. So the first thing that I'm going to have you do is I'm going to have you set up your calculator for polar graphing. So I need you to hit the mode button on your graphing calculator. Mode button. That's kind of up here, top left-ish corner. Hit the mode button. Make sure you're in radian mode, not in degrees. I know you've had experience toggling back and forth between radian and degrees. Here's what's going to be new. You've been in function mode this whole time, X and Y. You're going to arrow down to here. You're going to arrow over to polar mode, and you're going to hit enter. Next, I want you to set up your window. So now I want you to hit window, really up top left up here. Hit window. Now, when you hit window, this is what you're used to. You're used to seeing an X-min, an X-max, and an X-scale, and a Y-min, and a Y-max, and a Y-scale. That's just like normal. Make your X-mins and maxes about -5 and +5. So we want far left to be a -5. We want far right to be a +5. And I think we'll count by ones. Y-min, let's make our lowest a -5, and let's make our highest a +5. And you can count by ones there on your Y's. Here's what's new. Because you switched to polar mode, you now have thetas to deal with in your window. So what we're going to do is we're going to look at how does the graph look when I start my angle at 0 and look, picture the graph that you're used to. Don't we go from 0 to 360? We're going to start our angle at 0 and we're going to revolve it, rotate it all the way around, all the way through 1 pi, all the way back around to 2 pi. So we want to start our angle at 0, we want our maximum angle to be 2 pi. So literally, I want you to type in 2 and then use the pi button. The pi button is over here above your exponent button. You have to use second to get up there. So type in 2 pi right there. And the moment that you hit enter or arrow down, it's going to change your 2 pi to a decimal, which is fine. And then for theta step, then this is interesting. When we type an equation in and when we hit graph, you're going to watch it draw a rose or a cardioid or whatever. You're going to watch it draw that. And we can either, excuse me, it can either draw it super fast or it can kind of draw it slowly. Well, I want you to kind of draw it slowly. This right here controls how fast your calculator graphs the curve. So whatever it's set at, let's just change it to about 0.05. It controls the speed of my calculator's drawing. Okay, let's go to this one next. So the next thing I want you to do is do table setup. And we're going to do that. It's right above window. So you're going to go second and then up here to table set. I want you to put table start 0. Okay. The next is what we're counting by. And hold on just a second. Put your calculator down for just a second. I want to show you something. What do we want to count by in our table? So I'm going to pull up a table kind of in the back. You don't have to write this down. You'll have time later to write this down. I just want you to understand how you're setting up your calculator. So see this table? It says, hey, let's look at all these angles. Don't these angles look familiar to you? Those are all common angles. So what we want to do is on our calculator, when our calculator shows us a table, we want it to show us these common angles. However, we're going to tell it to start at 0, but what do you want your calculator to count by? So what do you want it to count by to show you this angle and this angle and this angle and this angle? Well, the problem is we have all these different denominators. We have different increments here. This is 30 degrees, 45 degrees, 60 degrees, 90 degrees. Those are different increments. So here's what we're going to do. We're going to look at all of these denominators and we're going to figure out what is the lowest common denominator out of everything that's showing. A 2 and a 4 and a 3 and a 6. Lowest common denominator that all of them go into evenly? 12. So let's change these to a denominator of 12. So think about this for a minute. This as a denominator of 12 is 2 pi over 12. Denominator of 12, 3 pi over 12. With a denominator of 12, 4 pi over 12. 6 pi over 12, 8 pi over 12, 9 pi over 12, 10 pi over 12, and of course, 12 pi over 12. And you can see that the increments are different. Here we jumped up by 2 pi over 12. We went up 1 pi over 12. We go up 1 pi over 12. We jump up 2 pi over 12. See how the increments are different? So, back to our table. You've still got your calculator handy. Table setup. Here's what I want you to do. We're going to start our table with an angle of 0, and we want to say count by 1 pi over 12. So you need to type in pi over 12 right here. And once you do that, and you push enter or the down arrow, it's going to change it to a decimal for you. We want to count by 1 pi over 12. And then independent and dependent, you want to put these on auto. What this does, it automatically supplies all the values in your table. They're just going to appear there. They're going to start with 0, and each new line is going to be another pi over 12, and 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 so on. Okay? And then for zoom, and this is kind of optional, when you graph, if you do a zoom square, it's going to, since the window on your calculator is rectangular, sometimes you get kind of a squished image of your graph. And if you set this to square, it'll kind of unsquish it and make it nice and properly proportioned. All right, so now what I'm going to do is I'm going to switch over to my graphing calculator and I'm going to set up what I just showed you. So if you're good with your setup, you might just want to fast forward through this next part. I don't know. But I'm going to switch over. If you missed anything, I'm going to switch over to my graphing calculator. And here I go. I'm going to make sure you can see it, first of all. There we go. Okay, I'm going to go to mode. I'm going to go down to function, over to polar, and I'm going to hit enter. I'm going to go to window. My theta min is already 0. My theta max, oh, just for fun, I'm going to type it in. I'm going to type in 2 pi. See, 2 pi. And when I hit the down arrow, it changed it to a decimal for me. Theta step, I'm going to go with, I think I said 0.05. Remember, that just slows down our drawing because there are some things that I want you to pay attention to while it's going. And then I'm going to, let's see, I can go, I don't need that to be that big. I can go -5 and +5 and -5 and +5. Now, I'm going to set up my table. I'm going to have it start at 0. I'm going to go down. I want to count by pi over 12. There we go. Now, here's what's cool. Hit your y equals. It's not y equals anymore. It's r equals because you already told your calculator, let's graph in polar mode. So now you know what it's expecting from you? It's expecting some sort of trig expression like sine or cosine or tangent or whatever, and it expects a theta from you. And you're like, oh no, I don't know where theta is. All I know where is x. That's all I know. Good news. Your x button that you always use for your variable, it can be x, or t if you're in parametric mode, which we're not. It could be theta if we're in polar mode, which we are. So anytime I hit that variable button, it's going to pop up with a theta instead of an x because we're in polar mode. It just knows what we need. Alrighty. So let's go ahead and graph this first one in our notes. We're going to graph the polar equation 1.5, and that's supposed to be a plus right there. I don't know if it is or not. So let's graph this. Ready? Type this in with me. 1.5 plus 1.5 sine of theta. Sine, see, gave me a theta. And we'll go ahead and graph it so you can see what it looks like. Woo, that was fast. Oh, I know why. My computer goes so quickly. Okay. Make a slight change here, but I don't want you to see what I'm doing. Okay. So one more time. I slowed mine down a little bit. There we go. Notice, I bet it didn't start where you thought it was going to start. I think it started right here on the x-axis and went around and did that and finished off there. All right, so I've shown you how to graph it. Now, in your notes, what we need to do is we need to fill out this table of values right here. So, I'm just going to show you something here real quick. Stay where you are in the notes. I'm going to show you something. If you were to do this by hand, which you're not, if you were to do this by hand, you would actually sub in 0 for theta. And I pulled this one up because this one's an easy one to show you. Sub in 0 for theta. Ready? 3 times 0 is 0. What's sine of 0? It's 0. Take that times 4. What do you get? You get 0. Next one. Sub in pi over 6. Ready? Put pi over 6 right here. Times it by 3. You get pi over 2. Sine of pi over 2 is 1. And 4 times 1 is 4, last time I checked, right? Pi over 4, sub it in. I don't want to, but that's what's happening. That's what our calculator is doing for us. So back up to here. Get back to my graphing calculator. Let me show you where these values come from. I'm going to go to table. Second table. All right. So, in your notes, you ready? It says when theta is 0, what's r? Well, that's right here. When theta is 0, r is 1.5. Write it in that box right there in your notes. The next one it wants is pi over 6. I'm sorry if there's a glare, but keep in mind, we're counting by pi over 12. So this is 0. You know what this is? This is 1 pi over 12. I don't want that one. I don't want you to write 1.88. I want pi over 6, which is 2 pi over 12. The next one is 3 pi over 12. The next one is 4 pi over 12. 5 pi over 12. 6 pi over 12. Okay? So pi over 12, that's not a common angle. We don't use that angle very often. In your table, in your notes, it wants pi over 6. So we're going to use the 2 pi over 12. Use this. This is 2 pi over 12. Write this down for r, 2.25. The next angle, after pi over 6, it wants pi over 4. Well, what's pi over 4 with a common denominator of 12? It's the next one. So the 1, 2, 3, including 0, 1, 2, 3, 4. The fourth one down is pi over 4, and that's 2.56. Write that in the middle box. The next one it wants is pi over 3. Pi over 3 is 4 pi over 12. So the next one you need to write is rounded, 2.8. Now it goes to pi over 2. So I'm here. I don't want the next one because that's 5 pi over 12. I do want this one because it's 6 pi over 12. And write 3 in that box. Okay, so just keep in mind, each row is a new pi over 12. 0, 1 pi over 12, 2 pi over 12, pi over 6, 3 pi over 12, pi over 4, 4 pi over 12, pi over 3, 5 pi over 12. We don't use that one very often. 6 pi over 12, pi over 2. 7 pi over 12. We don't use that one very often. 8 pi over 12. 2 pi over 3. And so on. Okay, so hopefully you've got your table filled out, and I'll go back to the notes just to make sure you've copied down the right values in just a minute. Now, in the notes, the next thing it asks for is what's the necessary theta range? So I want to go back to the graph. I want to know from start to finish, did it take from 0 to 2 pi? Did our angle have to go all the way around to 2 pi in order to complete the drawing of this graph? So, let me try something here. I'm going to graph it again. I'm going to slow it down even more, And I want you to, I'm going to show you how to watch for something. Okay, now before I hit graph, here's what I want you to watch. Kind of keep an eye on the graph, where it starts. And then I want you to look up here in the top corner, the top right corner of my calculator. I think you're going to see a little circle, I think, and this little yellow circle. And it's going to go around and around and around to say, I'm still thinking, I'm still thinking, I'm still thinking. And when this little yellow circle stops spinning, that's my calculator's way of saying, okay, I'm finished. So remember how our window said let's go from 0 to 2 pi? I want to know if it uses all of that thinking time to make the graph. Let me kind of show you what I'm talking about. Ready? I'm about to hit graph. See, I'm thinking, I'm thinking, I'm thinking, I'm thinking. The moment it stopped thinking, it finished the graph, which tells me it took all the way from 0 to 2 pi to draw that picture. Because what happens sometimes is your picture gets finished and your calculator is still thinking. And occasionally it will redo itself before saying, okay, I'm done. And how long does it go? As long as you tell it to. I told it to go from 0 to 2 pi. That's how long it will think, but sometimes it doesn't take that long to complete the picture. So it stopped thinking and completed the picture at the same time, so it took from 0 to 2 pi. And so in the notes, I'm going to go necessary theta range. It took all the way to 2 pi to finish the picture. And double check, make sure you wrote down the right values in your table. And this is a cardioid. Okay. Next one. I'm going to type this in my calculator. I'll go over kind of quickly again how to get the values in the table, and we'll graph it. And I'll show you again to make sure that it takes up the whole 2 pi to make that happen. And we can either look at it after it's graphed, or we can look at the equation, and it's going to be a limosome. Okay, so let me go back to my calculator. Let me get it typed in. 1 minus 3 cosine theta. Okay, ready? I'm going to hit graph. We're going to watch it graph. We're going to watch the I'm thinking sign up here. My window is still set at 2 pi. I'm thinking, I'm thinking, I'm thinking. Done, done. So it took all the way to 2 pi, because that's what my window is set at. Took all the way to 2 pi to draw that. Let's check out the table really quickly, because you're going to want to pull your values off of that. Notice in the notes, it doesn't want weird angles like pi over 12. It wants all common angles. So the first R value you're going to write is -2. This is 1 pi over 12. Skip this. 2 pi over 12. Write it. 3 pi over 12. Write it. 4 pi over 12. Write it. 5 pi over 12. Skip it. 6 pi over 12. We should be at pi over 2. Write this. Does it go on? It does. 7 pi over 12. Skip it. 8 pi over 12. Write it. 9 pi over 12. Write it. 10 pi over 12. That's 5 pi over 6. Write it. Oh, and I need one more. Six, 7, 8, 9, 10, 11 pi over 12. We're going to skip that one. 12 pi over 12. Write it. Okay. back to the notes. Let's just double check and make sure you copied down the right values for the table. Pause the video if you need to. Moving on to the next example, example 3. This is getting a little bit redundant, but this time it graphed our rows. And just double check and make sure that you pulled the right values off of the table. Ooh, tricky. This time it did ask for 1 pi over 12, and 2 pi over 12, and 3 pi over 12, and 4 pi over 12, and 5 pi over 12, and 6 pi over 12. Pay attention. All right, now I'm going to show you one that doesn't take the whole time to graph. So let's type this in our graphing calculator and I'll show you what to look for as it's graphing. We're graphing 5 sine 3 theta. Clear. 5. Ready? Done. See, it's still thinking. I knew that would happen. I knew I would choose one that was just way too slow. It's like watching grass grow. But here's what you're going to see eventually. It's gonna finish. It's gonna finish. And this guy's gonna say, I'm still thinking, because you know what it's doing? It finished from 0 to pi. But it's still got to go all the way to 2 pi because I told it to in the window. And it just kind of, it retraces over itself. Yeah, I set that too slow. Sorry. I'm not waiting on that. So for this one, just say that it goes from 0 to pi. That's how long it took to make the rows, and anything, all the angles beyond that, it just traced over it one more time, okay? Now, you do kind of need to know this. So what does the number out in front do? The number out in front, it determines the length of the petals. It's kind of like when you had a number out in front of your function and it did a vertical stretch. It's kind of what it does here. It's kind of like a vertical stretch, but it's not a vertical stretch. It's a petal stretch. It's stretching the R, the length of the petal. If you have a number inside here, what does that do? That determines the number of petals. The number out front determines the length of the petals. The number inside determines how many petals are in my flower. And this is kind of cool. If this number in here is even, how many petals do you have? Well, you have to double the number to find out. So if this were a 4, it would have 8 petals because 4 is even. In this example, this isn't even, it's odd. So if n is odd, it's just straight up the number of petals. This is odd. My flower has 3 petals. Okay, we're about there. Hopefully you're getting the hang of it. Can you look at the equation up there? And yes, you may refer back to your notes. Can you identify what type of curve it is? It's a limacone. Limacone doesn't have petals, so that's not applicable. Graph it on your graphing calculator, see what it looks like. Match it with the correct picture. Remember how your window was set from 0 to 2 pi? Did it take the whole time to draw the picture? Yes, it did. So what was the necessary range to complete the picture? All the way to 2 pi. All right, without a calculator, can you tell me what kind of curve it is? Yes, you can look at your notes. It's a rose curve. It has 3 petals. It's odd, so it's straight up just the number of petals. The next one is a cardioid. yes, you may refer back to your notes. Petals, not applicable. To fill out your table, use your graphing calculator. So you've already got your table count set up by pi over 12 intervals. Type that in. You want your angle, you want the value of r when this is 0. Skip the first decimal and go to the next one, which is 2 pi over 12, and write it down, and so on and so forth. So do that on your graphing calculator and make sure that yours matches mine. And then on your next equation, you should have here I skipped this one, my bad. Necessary theta range. What you'll see is it made this graph. Let's see, R was 4. So it made the graph, and it only took it drew this whole graph to here. And then my calculator was still spinning, and it redrew it, the whole thing. How do I know it needed to go to pi and not 2 pi? Well, easy. Just change your window. So if you think, you know what? I think my calculator was still thinking and the picture had already been drawn. Change your theta max to pi and see if the picture stops drawing the same moment your calculator stops thinking. Okay, and the necessary theta range for the next one was, it took the whole time, 0 to 2 pi. Whew, a lot of info, but it's really a lot of calculator usage. So I just encourage you, play around with your calculator. Let your teacher know if your calculator's doing some weird things, and we can help you get set up to where you can graph these.